particular port. You say, okay, that's a interesting pattern. But now if you see the same pattern on more than, let's say 5 honeypots, then you know, okay, well, that's strange. I mean, there must be an automatic program running there. Because, all these honeypots, they are not necessarily related. Right? They're just in the same address segment that you have, the IP segment. So why would they have the exact same pattern across multiple honeypots? So that must be an automatic program, which means there could likely to be a worm, right? So the kind of interesting events that we actually gather, we use some domain knowledge to analyze what a worm would likely do, right? For example, it would come in, explore, and then go out and get some they call it egg, meaning the attack programs and so on and so forth. So there are multiple points here that you can actually use to detect some interesting activities. For example, you can detect buffer overflow, some algo network activity, or also if the attack program is being stored at the hard drive, then you will see some possible disk activity. Okay, so essentially all these are interesting activities that the honeypot can actually capture. Okay, so meaning memory events, disk events, and network events. All right. Now these events by itself, they indicate some intrusion. Obviously, by definition, nobody should be doing anything on the honeypot. So anything there is bad. But again, we are only interested in a particular problem, meaning the worm, right? So the point is that there are a lot of event data actually doesn't contribute to the analysis of worm, right? So only some of those would be useful. But again, the argument here is that because we're looking at the alerts from honeypot, this already has very, very high base rate. We are not looking at the raw traffic to your network. Right? The raw traffic network may not have some attack traffic, but the events that we capture in a honeypot, they are very good candidates. Right? So again, the argument is that when you look at the event data from the honeypot, the base rate is very high. So you have a much better chance of finding out whether there's a worm or not. So essentially, how do we correlate a honeypot event with some other activity on a honeypot? So suppose here at this particular time, we see the outgoing traffic. So we want to correlate activities in the preceding time windows that can explain the current activity. So again, we are not using any hard-coded rules to do this. We attempt to do it automatically. So I'm going to get into the details of the analysis. But the point is that the intuition here is that the more recent events on the honeypot will probably explain more about the current outgoing activity. So that's the intuition. So we can use some logistic analysis to actually attempt to explain and figure out whether we can actually analyze and conclude that, for example, this activity at port C actually triggered the outgoing traffic, for example. And if the same patterns are discovered across multiple honeypots, then we think, okay, there could be a worm. So essentially, this shows that many observations across multiple honeypots actually combine to make the detection, right? So essentially, one insight here is that suppose you have some inconsistent patterns. Suppose you see outgoing traffic across multiple honeypots, but then the patterns are not consistent across multiple honeypots. Then it's likely that it may not be caused by automatic program. It could just caused by some random hackers, right? But then of course the question is that what about if I write a very smart worm to do this? Yes, that's possible. We're going to work on that. But the thing is that for all the smartness about worm, there's arguments saying that how do you encode that kind of smart logic into the body of worm? Think about if a worm writer, of course you can do a lot of a lot of things. But then you also want to keep the worm body to be relatively small. So if you encode a lot of logic, then your worm payload would likely to be actually very big. For example, there's a famous study on routable worm, meaning that suppose I don't have scanner worm. I know exactly which edges is routable. It turns out that to encode that knowledge requires a huge amount of space, right? So obviously, each worm payload has to carry that knowledge around. But if in order to carry the knowledge around, the cost is too high, then the worm writer may not do that. So that's why the worm tends to be stupid, because they want to spread very fast, very, very lightweight, right? So I mean, there's also a trade-off there, meaning how smart you can be being a worm, and how easy it is for the ideas to catch you. So anyway, so let's talk about the correlation analysis. So essentially, we're interested in this problem where the honeypot is awake or not. Suppose you say, we use the variable y to represent whether a honeypot is sending out outgoing traffic or not, meaning awake or sleep, right? So then we say, awake is 1, otherwise it's 0. Then we want to say that whenever the honeypot wakes up and sends out outgoing traffic, what are the contributing what are the activities that contribute to that kind of outgoing connection, and then how so the x would be representing the contributing activities, and then beta would be how much contribution each activity actually would give to this outgoing traffic. So we use logic analysis essentially because it's a binary variable, and essentially using logic analysis essentially try to find out how likely the axis, meaning the activities happening at the honeypot, contribute to the fact that the honeypot now sends out outgoing traffic. Okay, so this is standard techniques, and so the way that we apply this is that the x here essentially is the inverse distance in time. Suppose I see a outgoing traffic, okay, and so let's say I see outgoing traffic at this particular time. Then I look back, let's say within 2 days, okay, and then there'll be a lot of activities. Let's say there's activity at port I. Then the distance in time from this outgoing traffic versus activity at port I would be dt, right? So 1 over dt would be the x value. So essentially, we're trying to explain whether the incoming traffic or some event at port I would actually explain the outgoing traffic at this particular time. So then we just apply logic analysis to compute the statistics, for example, the beta values. So that will tell you whether the traffic, the event at port I actually contributes to this outgoing traffic. So, and we actually, after we published paper, I found out, okay, there's actually an oversight in terms of how we do this. So ideally, what we should be doing is that we should have 2-level correlation. The first level correlation is that for each honeypot, we correlate the outgoing event with the other events at the honeypot. And then the next level correlation would be you sort of correlate across multiple honeypots to see whether the same patterns actually is there. But then my kind of oversight, my student actually did the following. He essentially got all the events across all the honeypots together, and then try to use that in logic analysis. So this would be, for example, this would be the observing outgoing traffic at one honeypot, and then from there he would get all events from all other honeypots. That would be all the xij here, and then do correlation. So he argued that this would work, but there could be some false positive, meaning that suppose you may be able to actually correlate a particular attack here with some outgoing traffic